Hello everyone, today we will be looking at quantitative electrolysis, where we will be calculating the mass, all right, or volume of your element that is being formed from your electrolysis. So first, if we were to recall back, electrolysis is defined as the decomposition of the electrolytes to its constituent element. So if you were to decompose NaCl molten, you will get Na solid metal at standard state, Cl2 gaseous state, okay? That will be the element in standard form, okay? Standard states under standard condition. So the first one we're going to look at is some simple cation calculation, okay? So let's look at the Winter 20 paper 41. So we start off with an easy question first, and then we move to a more medium difficulty. Identify the substance liberated at the anode and at the cathode during the electrolysis of the aqueous sodium sulfate. Now, if you have not learned about electrolysis, perhaps I will just leave a link around the video here that you can go and click and watch what is electrolysis before you learn how to calculate what is the mass or volume that is being formed. Okay, so first for anode, okay, anion move to the anode, remember? And second, cation will move to the cathode. Okay, it is fixed, okay? And then anode is always oxidation, cathode is always reduction reaction, okay? So now when we look at sodium sulfate aqueous, okay, you have an aqueous, which is a competition of H2O for the respective electrodes. So for the anode, okay, for the anode, we have two ions that is competing, which is the sulfate and the hydroxide. And for the cathode, we have the two ions that is competing, which is the Na plus and the H plus. Now you need to refer to your data booklet. All right, so please go and open your data booklet. All right, now refer to the page where you can see the standard electropotential. Now, so first, we will look at which ion that will be discharged at the anode. Now, in general, sulfate and nitrate will not be discharged. All right, so by status quo, hydroxide will be discharged. And if you refer to the E value that is having a positive 0.40 using the Cambridge standard electropotential, all right, you will get this equation here. So this will be E value at positive 0.40 version, okay? So this is the hydroxide, all right, that will undergo discharge. What is the substance liberated? So your answer is hydroxide will liberate oxygen gas. Okay, sulfate, nitrate normally are not discharged. Okay, and for a general rule, we will always pick the more negative E value to be discharged. Let's look at the cathode, cation. So for the cation, a general rule is we will pick the more positive. Okay, the more positive. So if I were to write the E values for the sodium and the hydrogen, if I'm not mistaken, sodium will have a 2.71 positive and hydrogen is 0.00. Between the two, oh, sorry, my mistake. Sodium is negative 2.71, right? Negative 2.71, around them, okay? Now, among these two values, the hydrogen will be more positive. Hence, the more positive E value cation will be discharged. So what is formed? Hydrogen gas. Okay, so that is an easy one. Now we're going to go into the calculation. So when molten sodium chloride, this is something else. Molten, that means there's no aqueous. That means it's a very straightforward Na plus Cl minus electrolyte. Chlorine is liberated at the anode. That's correct. Because chloride is an anion. An ion will move to the anode. Okay, and sodium will be liberated at the cathode. A sample of molten sodium chloride is electrolyzed for 1.5 using a current of 4.5. Calculate the volume of chlorine and the mass of sodium that are liberated. Okay, so this is quite straightforward. First, we want to calculate what is the total quantity of charge. So the quantity of charge is defined as the ampere or current times or multiplied with the time in seconds. So the current we use is actually 4.5 ampere, and the time that we use is 1.5 hours. We need to change to minute and change to seconds. So if you calculate this, you should be able to obtain an answer which is 24300. All right. C, Coulomb, quantity of charge. So you need to use the formula Q equals to ID. So in your electrolysis experiment, you only pass 24,300 quantity of charge. Okay. Now you need to look at the equation for chlorine. So for chlorine, if you go to the standard electrode potential, okay. So what we can see here is we need 2 Faraday to liberate 1 mole of chlorine gas. So theoretically, 2 Faraday will be able to give you 1 mole of chlorine gas. It also means 2 times 96500 are able to give you 1 mole of chlorine gas, which is 24 dm cubed. Okay, now, so how much quantity of charge have you passed, all right, through your electrolysis? You only pass through 24,300. So 24,300 will give me how much moles of chlorine molecule, all right? So let's do a calculation. So you only form 0.126 mole of chlorine molecule. So if you want to change it to volume, you multiply it with 24 dm cubed. Hence, the volume of chlorine is 3.02 dm cubed. Okay, so that will be for chlorine. Now, I will use a different color for sodium, all right, to make it neat. So for sodium, we take out the equation for sodium, Na plus and E minus to give Na. According to this equation, 1 Faraday is needed to form 1 mole of sodium metal. So it also means 96500 quantity of charge will be able to give us 1 mole of sodium metal, which is 23 grams. Okay, so you pass 24,300 in your experiment. So how much mole of sodium metal is being formed? 0.252 moles. And if you want to know the mass that's being formed, you multiply by 23, which is the atomic mass, 5.79 grams. So you form or deposited 5.79 gram of the sodium metal. All right, so this is a very, very straightforward question to start off with. Okay, so now let's proceed with another question. Okay, anion. Okay, so let's look at summer 2042 question 8. So they give you a fuel cell, okay, that can generate electrical energy. A methanol oxygen fuel cell can be used as an alternative to hydrogen oxygen fuel cell. When the cell operates, the carbon atoms in the methanol molecules are converted into carbon dioxide. Calculate the volume of CO2 in centimeter cube form when the current of 2.5 is delivered by the cell for 30 minutes. Assume the cell is operated at room condition. So what is nice about this question is that they have given us the equation. So what we can see from the equation here is we need 6 Faraday to give us 1 mole of CO2. Okay, so theoretically, 6 times 96500 is 57,900. All right, will only give me 1 mole of carbon dioxide gas. Correct? Okay. Now, so let's calculate in actual case in your experiment using Q equals to IT. Okay, how much quantity of charge have you passed? All right. So whatever we've been doing just now is to find out theoretically, according to the equation, theoretically, how much quantity of charge is needed. So we have calculated 57, 9,000 to give one more. But in your actual experiment, you only pass 2.5 times 30 minutes converted to seconds. You only pass through 45,000. Sorry, 4,500 quantity of charge. So 4,500 quantity of charge is how much moles of CO2? You only managed to liberate 0.0777 moles of CO2 gas. All right. So given the mole, you can calculate what is the volume. So 0.0777, you times 24 dm cube and times 1,000 to convert it to cm cube. Correct? So therefore, the final answer would be 1865. Let me see where to put my decimal place. Here. 186.5. Okay. So let me just check my calculation one more time. Yes, that's correct. Okay. So 186.5 centimeter cube. All right. So that is a anion, a simple case here where they gave you the equation. Now let's look at a third example here. So this time we're going to look at anion, but we have to choose the correct equation to be discharged. Okay, so let's look at the part A. Identify the substance liberated at the anode and the cathode during the electrolysis of the saturated. Yes, I picked this question because there's a saturated. Now, so let's highlight the word. Saturated also means concentrated. Okay, KCl, that means you got K plus and Cl minus. And you have hydroxide and you have H plus. Okay, where did I know to put H plus and OH? It's because they use EQ. So now you have two cations competing for the cathode and two anions competing for the anode. Okay, now when you say saturated, it means you have high concentration of K plus and high concentration of Cl minus. So when we play with saturated, we will pick the more concentrated anion with higher concentration to be discharged. Okay, so at the anode, okay, chlorine gas will be liberated because chloride is a higher concentration present in the solution. Okay, even though his E value is more positive, because normally we will pick the more negative E value to be discharged. So without the concentration or the concentrated or the saturated word, if you just play with aqueous, hydroxide should be discharged instead of chloride. But because you use saturated, then we will pick the more concentrated anion to be discharged here. Now, for the cation, it's not the same. For the cation, the concentration does not affect the selectivity. Okay, we do not say that because K plus ions is present in high concentration, therefore K plus ion will be discharged. No. So if the cation is more straightforward, we will go back to status quo. We will pick the more positive E value to be discharged. So I think potassium is something like negative 2.92 around there, but it's a very big negative number. We will go back to square one, where we will pick the more positive cation to be discharged, regardless of the concentration. You have to know, all right? So hence, hydrogen gas will be liberated over here. So let's do the calculation below. When dilute sulfuric acid is electrolyzed, oxygen is liberated at the end of, they told you, and this is something similar to our first question, all right? So remember I said, normally sulfate are not being discharged. So dilute sulfuric acid is electrolyzed for 15 minutes using a current of 0.75. Calculate the volume of oxygen. So now you have to choose the correct equation to be discharged. Now I have extracted the two related equations from the standard electrode potential, and I attach it here as you can see in the pink color table box here. So first, you need to know that sulfates will never be discharged, nitrate will never be discharged under normal circumstances. Okay, so if you know this rule, then you're only left with one answer, which is called hydroxide will be discharged, and he liberate oxygen gas, which fits the question because they said oxygen is liberated at the anode. Okay, now, so even if you do not know that sulfate will never be discharged, even if you do not know about that, you will go back to your so-called theory. When it comes to anion, we will pick the more negative anion to be discharged, which still lends us to decide or to pick hydroxide to be discharged. And you're still going to come out oxygen gas. All right. So based on this equation, right, you know that theoretically 4 Faraday, because there's 4 electrons involved, all right, is needed to form 1 mole of oxygen gas. So theoretically, 96500 times 4, this will be 386,000 only can liberate 1 mole of oxygen gas. Okay, let's calculate in your experiment. All right, how much did you pass? You passed 0.75 ampere times 15 minutes, convert it to seconds, 675 coulomb. So you only pass 675 coulomb, then question mark, how much more are you obtaining here? So this, you only liberated 1.75 times 10 to the power negative 3 moles of oxygen gas. So once you get the mole, you can go and times 24 dm cube and convert it to centimeter cube. And the final answer would be 42.0, okay, centimeter cube. Okay, yeah, so that will be the third example. All right, let's look at the more challenging question. I'll consider this as medium difficulty. This is taken from March 21. All right, so iron oxide can be electrolyzed using inert electrodes to form iron metal. Write the half equation for the reaction that occurs at the anode. Okay, now anion moves to the anode. So anode is forever oxidation, that's the rule. So your half equation is your anion will move to the anode, and anode will undergo oxidation, which is donating electrons. Okay, so 1 oxygen donate to 2 oxygen or 2 oxide donate 4 electrons in total. Okay, now next, calculate the maximum mass of iron metal formed. When iron oxide liquid, this is molten, L means molten state. That means there is no AQ, that means there is no competition between the cation and the anion. You're the sole cation and you're the sole anion, all right? And it was electrolyzed by 6 hours with a current of 50 ampere. Now, so first, we have 1 Fe2 plus and 2 Fe3 plus. So if you go to the standard electrode potential, right, Fe2 plus requires 2 electrons, okay, to form iron metal. You only got 1, okay, so you need 1 Fe2 plus. And now Fe3 plus, okay, Fe3 plus requires 3 electrons to form Fe metal. Okay. Now, so over here in this example, you have 2 Fe3 plus. So that means you times 2. Now, so total over here, how many so-called electrons do you need? All right. You need 2, and then you need 3, and you need another 3. Okay. So total, you require 8 electrons, which also means 8 Faraday. Okay. To deposit 3 moles of iron. Okay, because the second equation times 2. Now, in your experiment, Q equals to IT, where I is your ampere 50. Now, time is 6 hours, convert to minutes, convert to seconds. So the quantity of charge passed is, whoops, sorry, not 30, 60. Let me just erase. 6 hours times minute times seconds. Okay, so now then your quantity of charge passed is 108,000 coulomb. So that is the total quantity of charge that is passed throughout your experiment. Okay, now so theoretically you need 8 Faraday to give 3 moles. Okay, so now you form so-called you only use 108. Okay, so question, how many moles is obtained over here? Okay, so let's take the calculation. Calculate 108 divided by 8 times 96500 times 3. So we form 4.2 moles of iron. Okay, so if you want a mass, you times with the atomic mass of iron, which is 55.8, and the answer obtained 234.2 gram. Okay, so that will be the mass of iron form. So this one, they have 2 types of iron. All right, so therefore, you need to do it separately and combine total how many electrons are needed. All right, which is also the number of Faraday needed, which is 8F, or 8 Faraday is needed. Okay, now so that would so-called show how to calculate the total number of mass or volume formed from your electrolysis. All right, now if you're interested, maybe I will do another uploading on calculating backwards. Okay, which is, let's say now I give you the mass. All right, can you calculate the oxidation number? Can you calculate the time? Can you calculate the ampere? Right, and I will leave a link in the next video. All right.